Hello and welcome back to the Matlab course. This is part 2, and in part 2 we're going to be starting by doing some plotting. We're going to write some functions. In the first part we looked at writing scripts. That was a set of commands that we asked Matlab to do one after the other. This time we're going to write functions where we're going to ask Matlab to take an input from the user and then output something. So that's a small difference there. And then we're going to be looking at if statements, and then we're going to look at loops, for and while loops. And at the end, I'm going to give you a challenge in the shape of the collapse conjecture. So that'll be a little bit of an extended task for you towards the end of the session. Let's start by looking at plotting. So once again, all of this is on the GitHub repo. So if you head back over there, github.com/pecnet/course intro to Matlab, there it is. You can scroll down to part 2 and you'll be able to see in a sense, the script for what we're doing. Let's head over to Matlab as we do our first bit of plotting. So here we are. This is the last thing that we did in the previous session. So we can go ahead and create a new script. And in this new script, we're going to do plotting for the first time. You can go ahead and create a new script just by clicking the plus up here. There you go. Or maybe if nothing popped up here at all, you'd have to go to new script here or new here. Either of those do the same thing. You get a nice new window. We're going to do our first plot. Let's go ahead and save this before we start. I think it's always a good idea to save before we begin. That way you know what it's going to be called. Let's call this first underscore plot. Again, remember that we can't have spaces in Matlab file names, so we have to use underscores, and that's fine. First underscore plot.m. Actually, there's another important criteria for the name of your functions, or indeed any of the Matlab files. It's important, and maybe we'll see it later. It's important that you don't name your Matlab file the same as an inbuilt function. You can't call it something like sine or cos or even just plot, as we'll see shortly, because otherwise we end up overwriting Matlab functions. So obviously that begs the question: how do we know that how do we know that we're overwriting a Matlab function that's built in? And the answer is you don't. But by and large, you should be able to avoid this problem. We might talk about this again later. First underscore plot.m is a good way to go. All right. So we're going to do our first plot. Let's, along the x-axis, have the numbers from 0 to 10. Oh, trying to remember how to type. There we go. A semicolon to suppress output. And we're going to let y, this plot is going to be e to the x. It's going to be a nice exponential graph. There it is, y equals x for x. And then we're just going to plot x and y. So this is to set up a bunch of coordinates, right? X is 0 to 10. Y is e to the x for each of these x's, and then we're going to go ahead and plot it. It's as easy as that. If we go ahead and just click run, or remember pressing F5 does the same thing, then your graph should pop up somewhere. And I'm just going to drag it over so you can see what it looks like. There you go, so that should pop up somewhere on your screen. You might find sometimes that this window appears behind your Matlab window. So you might have to faff around with the windows on your computer to find it, but nonetheless, there it is. And there is a beautiful, beautiful plot. But it's not particularly smooth. So let's see if we can do something about that. You can see that it's got corners here, here, here. Of course, it's not very smooth because, well, we've only, these are the numbers x, 0, 1, 2, 3, 4, 5, 6. So we have all these coordinates. If we want it smoother, we need to have more values of x. So how do we do that? We need to Reduce the step size. Here we're going from 0 to 10. I want to go up in smaller amounts. So let's go up in steps of, what do you reckon? 0.1 maybe? Let's go from 0 to 10 in steps of 0.1, and now let's see what the graph looks like when I click run. Here we go. Merge nicer. There we go. And we can move this around. Now, depending on which version of Matlab you're running, if you're running one of the newer versions, if you put your mouse over the graph, then you can see a bunch of options come up here in grey. One of those is the hand function, and if you click on that, then you can drag the screen around a bit like that, and you can see the graph. If you're using an earlier version of Matlab, these are, I think, up here at the top in colour. It's all the same commands, but they're just in a different place. So you can also go ahead, have a play with these in a moment. You can zoom in, and that allows you to click and drag an area that might be of interest to you. Maybe we're curious about this corner here, and why wouldn't we be? Look at that. Very nice. So these are some options that are available to us. So that's our very first plot. Let's get you plotting something. And in particular, I want you to have a go at plotting these two things here. Firstly, plot the exponential plot as we just did, and then these are two challenges. Firstly, I want you to plot a sine graph for x between 0 and 2 pi. Right, now be careful. You want to make sure that your step size is small enough, otherwise you're going to get something very, very spiky, or I mean, that could also be fun. And then I would also like you to have a go at plotting a circle. And remember, this is how you plot a circle parametrically. Remember, x is cos theta and y is sine theta. If you have a theta that goes between 0 and 2 pi, that makes a circle with a radius 1. So I'm going to give you some time to do that now. We'll pause, and then I'll show you how I did it. Alright, so we're going to have a go at plotting sine x for x between 0 and 2 pi first. So let's head back over to Matlab. Oh, we don't need this anymore. I'm going to replace my my old plot. I'm now going to plot sine x, so no longer x of x, but sine x, and we're going from 0 to 2 pi. Maybe you figured out that 2 pi was just 2 times pi. There it is. Let's give that a go. Let's run that. And what do you know? There it is. Beautiful. Look at that. Well, okay, you've already seen it because you've done it yourself, but nonetheless, I think that looks nice. And then the second challenge was to plot a circle, and I showed you how to do, or I gave you the instructions for doing that parametrically. Let's have a look at doing that. So this time we have to have a theta, so we're going to let theta go from 0 to 2 pi. Again, also in small steps. And this time x is cos theta and y is sine theta. Semicolons to suppress output. All right, let's go ahead and run that. And ta-da! What do you know? A beautiful circle. Well, I mean, it's almost a circle. If you play around with window size, you can see that the axes stretch to fit the window. You might want to look up, there's a nice command that sets the axes to be equal, which you might want to have a look at. Let's take a look at this circle. Let's see if it is everything we hoped it would be. Again, if you're on a newer version of Matlab, if you hover over the graph, you can go and pick up the hand from up here. Older versions of Matlab, hands at the top. Let's have a look. Yep, that looks good. Looks like a circle. Looks like a circle. Oh, hello. What's going on here? There's a gap. Why is there a gap? I'm going to give you just a second to think about this, and then I'll tell you what's going on. So have a pause and think about why there might be a gap. Here's the code. All right, pause and then we'll come back. Okay, so why was there a gap? There's a gap because of what we're doing with theta. So in a circle, pressing the home button, you might have figured out, restores the view to what it was originally. In a circle, theta going from 0 to 2 pi starts over here, 0, all the way around to 2 pi here. But look at what theta actually is. If I type theta down here, then, okay, it starts 0, 0.1, 0.2, 0.3, 0.4, and so on, and it goes up to 6.2, which is almost 2 pi, but it isn't 2 pi, right? 2 pi, if we type it in, 2 times pi, is 6.28 compared to 6.2. So that's why you're missing the little bit of the circle at the end. So how can we fix that? Well, there's a couple of options. So one thing you could do is you could set the step size to be a multiple of 2 pi, or that is to say, is multiple the right word? I'm not sure. 2 pi divided by something. So that 2 pi is a multiple of this number. That's the better way to say it. Let's say that. So we could, for example, do 2 pi divided by 100, right? Then you know that 2 pi will be part of this part of the vector, and indeed, if you take the hand, you'll see that it connects up. But that's a bit ugly. There's a nicer way to do that, which is to use the command linspace. So I'm going to show you what that looks like. I'm going to comment out this row here. So you can comment out that entire row so that you sort of keep it without running it, if that makes sense. And you do that by adding the percent sign so that Matlab ignores it. You can alternatively do that by going up to the percent button here, which comments out the row for you. I can say theta equals linspace, right? So that's linear space. And let's see what the syntax is. So if we go ahead to try and type it, it gives us some insight as to what the format might be: x1, x2, and n. Remember that if we click on a function and press F1, then the help comes up for it. That's the previous help. Give it a moment; it'll launch the help for linspace. There it is. Eventually, there you go. Linspace x1, x2 returns a row vector of 100 evenly spaced points between x1 and x2, right? And linspace x1, x2, n generates n points. So the default is 100 evenly spaced points, but if you want to specify your own number of points between x1 and x2, then you can use this version here. I'm happy with 100 points. So let's use linspace 0 and 2 pi. Oh, can you see what mistake I've done there? I need to write 2 times pi. All right, let's run that. There's our circle, and what do you know? It is a nice circle that completes itself, as we would hope for. All right, so far so good. Let's try and make our plots look a little bit more exciting. Okay, so this was a circle, which was fine. I'm going to go back to I'm going to go back to our exponential plot. So this is nice, but I'm going to go back to our exponential plot where we had x going from 0 to 10 up in steps of 0.1. Y was x of x. So remember what this looked like. If I run this, you remember that's the exponential graph. There it is. What if I want to change how it's what it looks like? What if I want a red line instead? Well, that's easy enough. let's change the plot command. So we have x, y, and then r as a string. So we've got to put it in quotes. But if you want to change the color, R for red. Let's see. Ta-da! The line is now red. What if we want it dashed? Well, 2 dashes. What have we got? A dashed line. Most of the standard colours have single letter abbreviations. You are not going to win any prizes, although, I mean, you can always imagine yourself winning a prize if that's something that appeals to you, for guessing what letter G, or what colour G is going to represent. But if we don't want a line, but instead want just markers at the points, and then we can use O, and that puts a circular marker at all of the coordinates. Let's have a look what that does. All right, so now we've got a circular green marker, and it's quite a horrible shade of green, but don't worry about that. Let me zoom in on a bit. So now we've got green markers at every point, rather than a line that connects them. So there's a whole bunch of options with plots, and you can always, in fact, I recommend that you look at the help file again. If you go to plot, press F1, then there is a ton of stuff down here telling you how to do lots and lots of things, which are already which are pretty good. I think Matlab makes decent plots. It also tells you how to do nicer colours. That information's all down here. And so I have a few challenges for you. Actually, really just the one challenge. Here it is. The challenge is make your line as ugly as possible. Here it is. I want you to plot a magenta dotted line with a large line width. All right, so you're going to have to look in the help file how to change the line width. So far they've been quite thin, but I want you to find how to make the line width thicker. So that's a little bit of a challenge, but the information is in the help file. And I want you to have squares as markers. All right? So instead of circles, I want squares. So have a go at doing this, and then we'll come back and I'll show you how I've done it. So time to pause. So hopefully you enjoyed plotting the ugliest plots you could. It was a magenta dotted line with large line width and squares as markers. So let's see, magenta, the letter was M. A dotted line, I believe if we look in the help file, it was a colon that we needed for a dotted line. I think most of these shortcuts have, there's some easy way to remember them. Their shape looks a little bit like what they're supposed to be. Squares as markers, that's an S for squares. And then we want to specify a large line width. And looking in the help file, you would have found that you have to ask for line width, like this. So line width in quotes, comma, and then the line width that you want. Say, I'm going to pick 10 and see what that does. So this syntax is a little bit strange. We have X, Y, and then our sort of codes for the formatting. And then if you want sort of more advanced formatting, then you can ask, or you can give it an optional argument by saying the name of the property you want to change, in quotes, comma, and then the value. So you have to put it in pairs. And if you're thinking this is a ridiculous way to specify optional arguments, then you are correct. It's an old school, I guess it's an old school method. A little bit strange these days, but that's part of MATLAB's idiosyncrasy. Let's run this and see how wide that line is. Oh boy, That is pretty ugly. Let's have a look at what's going on here. So we have a dotted line. You can see the bits of the dotted line. That's the, I think that's these bits here. Yep, and you've got squares as markers, which are here and here, which is sort of crossing over the dotted line. Oh boy, it's really quite awful. What a mess. Okay, so that's pretty ugly, but that's that's what we get. So that's good. Let's go ahead now and try to make this graph a little bit nicer. We're going to stick some labels on it. That's not too bad. We're going to set our X label to be X. We're going to set our Y label to be X of X, right? That's what it is. And we're going to give a title to the plot. We're going to say, exponential growth is fast. Growth is fast. Surprise. Let's see that that's worked. Here it is. X of X, exponential growth is fast. All right. That wasn't too painful. We're now going to also, let's say we want to, instead of going from 0 up to 10, maybe we want to constrain we've plotted from 0 to 10, but let's just constrain the x-axis from going from 0 to 5 instead. And that's easy to do. We just use xlim. Xlim, I want to go from 0 to 5. So you put in 0 and 5 as a vector. So that's 0 and 5. Remember, that's a vector with two components, 0 and 5. And so the round brackets are because it's a function, and the square brackets is the vector. So that's why we've got two sets of brackets. Let's have a look at what that's done. Okay, this is interesting. So now x has gone from 0 to 5. The y-axis has automatically changed to fill the interesting part of the exponential graph. And that's worked quite nicely. So we're about to go ahead and try doing multiple plots on the same graph. But I'm going to give you a moment now just to pause and to add labels and change the x limits as I've done. So we'll pause now. All right, so let's do some multiple plotting. So the first type of multiple plotting is going to be multiple plots on the same figure. So let's go ahead and do that. So we're going to have our original plot, which is this one here. But we're also going to plot not just e to the x, but e to the 0.9 times x. So let's move this down for now, and we're going to call our original graph y1. Let's call the new graph y2. That's going to be 0.9 times x. Good. And then we're going to plot x and y1, and then we're going to try to plot x and y2. And for this one, I'm going to ask for a black line, black is K, and a dashed line as well. So that's what I'm going to ask for, normal line width. I'm going to get rid of these for now, so we have a simple command. I want you at this point to try this and see what comes up, and then see if it doesn't behave like you think it should. Try and figure out what it's doing, and then come back to the video and I'll tell you how to fix it. So try this now. Okay, so if you tried this, I think you will have seen that the graph that you get is just the black line, right? It's just the second thing that you ask it you asked it to plot. If you want to plot more than one thing on the same axis, you have to use the Matlab command hold on. So you hold on, and hold on makes the figure sticky. Anything that you plot afterwards, so you could have 100 more plot commands down here, they'll all stay on until either you finish the script or you type hold off. So you don't have to have hold off at the end, but if you finish the script, the effect is the same. Hold on makes everything sticky. Now let's have a look at what happens when we press run. Aha! So now we have our original hideous magenta graph here, and we have our dotted black line e to the 0.9 times x. That's here. And maybe we want to add a legend. That's easy enough. Let's ask for a legend. And then we just have to give the labels we want in turn in the order that we plotted them. So the first graph was e to the x, so I'm going to label it x of x. But of course you could label this whatever, you could label these Susan and Harry if you really wanted, but I don't think it would be terribly helpful. That's not 2x, it's 0.9x, isn't it? There we go. Let's give that a run. And what do we get? It is here. And so what do you see? The legend has appeared up here in the corner, and you can move the legend around actually by clicking and dragging it. You can move it to somewhere you'd prefer it to be. That's all possible. In fact, there are ways of coding this in here. If you check out the help function for legend by clicking legend and pressing F1 on the keyboard, you'll figure out what the code is, and you can see that it works quite nicely. If you don't like this way of creating legends, so here we've used the word legend, and then in order we've specified what each of the plots are. If you would prefer to attach these to the plot itself, then you can using display name. So just like we've used line width here, you can use comma display name xpex, for example, and then you only need to write legend here. You don't have to specify this. If you check out again the help file in plot, you'll learn how to do that. That's up to you. All right, something for you to try now. So far these have been linear plots. I want you to try and do the same sort of thing, but instead of using plot, I want you to use the commands log, semilog x, and semilog y. Right, so all the syntax is the same, you just have to replace the word plot. So have a go at that, see what they do, and then come back. All right, so I asked you to try log, semilog x, semilog y. Let's see what they do. So let's change plot to log, here and here. You'll notice, by the way, that these have to be the same if you're holding things on. Otherwise it breaks. Log for both. What do we get? All right, so we still see the curves, but now both axes have become logarithmic. All right, and that's probably not the right scale if we're playing with exponential graphs. What about semilog x? So again, using the same on both, copying and pasting out here. So now we have, with semilog x, we have a log scale on the x-axis, but not on the y-axis. But of course, for an exponential graph, what we really want is semilog y. That's exponential, or rather a log scale on the y-axis, linear on the x-axis. And with that, we get, look at that, beautiful, nice, straight lines, as you see, linear, log. So that's semilog y. All right, so suppose we have this particularly beautiful plot here, and we've decided that we want to save it. Matlab has a nice easy save function. Of course, you can just go up here and click save, and that'll open up the save dialog box, which is taking its time to show up, but I promise it'll be there. There you go. Now, by default, if you save the figure, it will save as a Matlab figure, which is a special Matlab file type, which is something that you can reopen again and edit. So in the same way that before we moved around the legend, you can still do that with a Matlab figure, and you can change a few other things. So that's quite flexible, but it's no good at all if you want to put it into a LaTeX document or into a Word document. Much more likely is that you'll want to save it in one of these formats. I mean, you have a big choice. You know, if you're from 1995, you'll enjoy the bitmap format. Good to see that's still in existence. If you like your LaTeX extremely old school, then you'll enjoy EPS files as well. But these have the advantage that the text in the figure is stored as text, so that when you compile your LaTeX document, the text matches the font and the font size that you specify in your diagram. It's a vector format basically, but it's slightly awkward to use. JPEG is a bad choice because of how they compress it. If you want to save it as an image file, go for PNG. It's a good choice. If you're happy with the vector image, then this is a good choice as well. SVG is nice. Or indeed as a PDF, which is probably the most common choice if you want to save it for LaTeX. If you save it as a PDF, though, word of warning, let's call this something like, I don't know, beautiful graph .pdf. So you've gone ahead and saved it as a beautiful PDF, and you might think that it might be perfectly cropped, but let me show you what it actually looks like. So it produces something that looks like this. So in fact, it prints it out on a sheet of A4 paper, or whatever is your default paper size. So you have this big white space around it, which is really annoying, to be honest. I mean, on the plus side, you can see that you can zoom in as much as you like. This was all dashed lines and squares, which is why it looks like this. But you can see you have a perfect quality image, but you also have all this white space around it, which is absolute rubbish. So on Mac, there's a command line or terminal function called PDF crop that you can use. You type PDF crop in the name of the file name, and it crops it for you, which is good. That's a nice, easy solution. The same thing also exists on Linux computers. I'm not sure what the Windows version is. It's just a quirk of using the PDF save. Okay, so we're now going to move on to writing and calling some simple functions. So far we have been writing scripts, which are just like this, bunch of commands one after the other. It's time to start writing functions. Functions take inputs, although we create them in a pretty similar way. So let's create a new file and let's save it. This is going to be a function, so it's going to take an input and output, but this is all going to feel very familiar. We're going to call this this function, and indeed the file, we've got to call it collapse_function, because all of this is about the collapse conjecture. Now, it's very important that if you're creating functions in Matlab, you have to save each function in its own file. I know that's really old school, but that's how Matlab is. Every function has to be in its own file, and the name of the file has to be the name of the function. Right? This is why you can't let the name of your files, any of your files, be the same as an inbuilt function like sine or cos or plot. It's going to break. So collapse_function. Let's write ourselves a function. Function y, that's going to be the output, equals collapse function of n. Right, so this is on the GitHub, but it's only 3 lines of code. Y equals 3 times n plus 1. That's what we're going to do. And then that's going to be the end of the function right there. So a little bit later, we'll play around with this function, and I'll tell you about the collapse conjecture and why this function is going to be interesting to us. We're going to make it more complicated as time goes on. But for now, this function is going to take in a number n. It does 3 times n plus 1, and gives that value to y, and then it outputs that value y. So that's the form, or that's the structure of a function. The output goes here, input goes here, and what happens goes in the middle, and we start it with an end. The tab here isn't necessary. If you've played around with Python, you'll know that tabs are important. They're not important in Matlab, but it's good for the soul, so I recommend it. So let's go ahead and save this. And I'm about to tell you to try this, but a word of warning: if you go ahead and try and click run, you're going to get an error. Let me show you what happens. Collapse function, not enough input arguments. Do you see it down here? Of course, because I haven't said what n is. To run the function, you have to type collapse function down here, and then you have to give it an input, in this case 5. All right, so I'm going to pause the video at this point to allow you to type this in, check it out, see that it works. Let's see whether you get the number that you think it should give you. All right, so hopefully then this worked. Collapse function 5 gives you 16. Nice. Now, I'm going to make this a bit more interesting by giving you a couple of more exciting tasks. I'm going to ask you to write another function, but this time instead of taking a number, it's going to take in a vector. So you can do this, but this should be a little bit more challenging. I want you to create a function. Here is the instruction here. I want you to create a function first and last, which takes in a vector v and returns the sum of the first element and the last element. So that's the sum of the first element and the last element. So I want you to do, that is to say, the first element plus the last element. And then I'm going to give you something to test it out with. Test it out with the command line, let in test vector equals 1 to 10, and running first and last on that. So in this case, first and last test vector, well, 1 to 10 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so it should return the sum of the first element and the last element, so that should be 1 plus 10, so it should return 11. So that's a little task for you to do now, and I'll allow you to pause the video to try that out. All right, so this is more challenging, but I think we can do it. So I'm going to create a new function, first and last, I've called it. And so function y equals first and last, and it's going to take in a vector v. I always think it's a good idea to put the end in before you do anything else. That way you know you've got the structure ready to go. Okay, so I want it to return. So I want the output to be the first element of v. All right, that's v1 plus the last element of v end. So I think that ought to do it. You might have another way to do it, maybe involving the sum function, or there are different ways to do it, but I think this will do the trick. Let's save it and check it out. First and last, fist, oh no, don't want that. First and last of 1 to 10. Our test vector, 11. There we go. So hopefully that worked for you nicely. Now we're going to change this so that, I'll show you the instruction here. We're going to change it so that it outputs the first and last elements separately. So sometimes when we have a function, we want it to output more than one thing. And that's slightly awkward in MATLAB, but not impossible. I'm going to show you how to do that now. So we're going to get it to output the first and last elements separately. So instead of giving one output, we're going to ask it to give 2 outputs, which I'm going to call first and last, but you could call whatever you like. You call them Y and Z, that's fine. And then we're going to say, well, first is V1, and last is Vn. Alright, so our outputs first and last are here, V1, Vn. Let's test it out again. So we can test it out again on our test vector. I know earlier in the script I asked you to let test vector equal 1 to 10. I didn't do that above, so I'll do that now. So let's do first and last, fist again, dear me. First and last of test vector. Let's see what it gives us. Does it give us first and last? It only gives us the first. And this you'll find is true of all Matlab functions. If you have multiple outputs, if you don't give a place for Matlab to put those outputs, all Matlab will return is the first one. All right. So if you want to capture all of the outputs, then you have to specify where you want to put them, which means you have to tell Matlab what you want to call them. So let's use first and last of test vector. So here I'm saying I want the variable first to be the first thing that first and last outputs, and I want the variable last to be the second thing that first and last outputs. So I do that, and now it says, aha, first equals 1, last equals 10. All right, so that's enabled us to pick out both things. So that's our first introduction to writing simple functions. We're going to come back, particularly to the collapse function, and make it more interesting in just a moment. But we're now going to move on to if statements, conditionals of course, in Matlab. And indeed, this is a standard programming thing. Ifs are quite important. So let's create a function that has an if built into it. Here we go. This is going to be the sign, that's sign, sign function. It's going to tell you the sign of a number. So if the number is positive, it's going to return +1. If the number is negative, it's going to return -1. And if the number is 0, it's going to return 0. So it's going to be a simple function that is going to tell you the sign of the number, sign. And we're going to call it sign underscore function. Just like that. So function, y equals sign function, and it's going to take x. Again, this is on the GitHub, so you'll be able to copy and paste this, but I'm going to type it out line by line so you can see what's going on. Again, I like to have my end ready to go. So we're going to put in an if. So if x is greater than 0, then y equals 1. This is the format we're going for here. Else, if x equals 0, y equals 0. Else, y equals -1. And that is the end of the if statement. So there's a few things I have to point out here. Firstly, if statements need ends. So you have your if, all your different cases, and then end. Secondly, let's talk about the logic here. If x is greater than 0, then y equals 1. Else, so the logic here is that if x is greater than 0, x equals 1, and that's the end. We don't have to check anything else. But if x isn't greater than 0, then it goes on to the next thing to check. That's what else if is all about. And you can have as many else ifs if you like, as you like. Else, if x equals 0, then y equals 0. Else, nothing else to check here, because else is the only other possibility, assuming, of course, we're putting in real numbers. The only other possibility is that it has to be negative. So there's nothing else to check. That's why there's nothing after the else. Y equals -1. And yes, this is two equal signs. When you're comparing two things in most programming languages, Matlab is one of them, you have to use two equal signs. Use a single equal sign to assign variables. X equals 2. You're assigning 2 to be x. But if you're asking, does x equal 2? X equals 2. So that's two equal signs for comparison. That's what's going on here. So with that, let's check out sine function and see whether it works. So I saved it, Control S, and then let's go ahead and try and run the function. Sine function of, I don't know, let's pick a number. 3, great choice. 1, nice. Okay, now pick a number between -1 and -10. -7, great, let's try that. Sine function -7 is -1, nice. Sine function of 0 is 0, good. So it looks like it works. I'm going to give you a moment now to copy and paste this and convince yourself that indeed it works by playing around here. And then once you've done that, I have a task for you. I want you to change Collat's function. So it first checks whether n is even. If n is even, then it lets y, the output, be n over 2. Otherwise, it returns 3n plus 1. So at the moment, it always returns 3n plus 1. I want you to check whether n is even. Now to do that, you're going to have to remember even means that it's of course divisible by 2. That means that the remainder of the number when divided by 2 is 0. Now in the first part of this course, I asked you to look up the function that gives you the remainder when you divide by a particular number. So you might have to remember back to that to figure out how to check whether a number is even. So go ahead, check whether n is even, and if so, return n over 2, otherwise 3n plus 1. So this is a bit of a challenge, so I'll take your time and ask if you get stuck, and I will pause the video here. Alright, so this is a bit of a challenge, I think. Let's have a look how I would do this. So in the Collat's function, I ask you to change this. So I ask you to say if n is even, so I'll give myself some space. So if n is even means that mod, or rem, you could use rem, that's fine. If mod of n2 equals 0, right, that means if n when divided by 2 is 0, so if it's even, then the output of the function y is n over 2. Else, right, remember with else, you don't put anything else after else because it's the else says in every other case, it has to be this. Else, y equals 3 times n plus 1. And if statements need n's. And, here's something we haven't discussed. Do you see how there's a squiggly red underline here on the equal sign? Let's hover over it and see why it's unhappy. Terminate statement with semicolon to suppress output. It thinks we've missed the semicolon off, and indeed it's right. Good. Let's save it and see whether it works. Let's try. So if it's odd, like with 5, it should behave as it did before. Collat's function of 5, 16. How about if I give it an even number? Like, I don't know, what's your favourite even number? 2, great choice. Gives us 1. Nice. All right. So now we're going to move on to looking at loops. Ifs are very important, but we're about to move on to loops. And there are 2 types of loops in computer programming. There is the for loop and there is the while loop. So this is this is section 4 in the online document. A for loop is when you know how many times you want to do something. Right, so maybe you want to do it 10 times or 100 times or 1,000,000 times, but you know how many times you want to do it. A while loop is when you want to keep on doing something while something is true. Or to say it another way, you want to keep on doing it until something changes, or something is true or something is false. So both of those can be useful. I'm going to first show you how to do a for loop, and then I'm going to show you how to do a while loop. All right, so let's go ahead and create a for loop. So we're going to create a new script, and we're going to call it squares up to. So we're going to create a script that prints out square numbers. Okay, not that exciting, but it's going to loop through the numbers 1 to 10, and it's going to print out that number squared every time. So we're going to call it squares up to, like that. So this is just a script, it's not going to be a function. Let n equal 10, and then we say, here's the loop. For I equals 1 to n, right? Then I'm going to ask it to display I squared. Right, so all this does, I'm going to say leave a comment to myself. So this squares I, and then it displays it on the screen. And then every 4 needs an end, and that's the for loop. So I will go round from 1 to 10. The first time round I will be 1, then I will be 2, I will be 3, I will be 4, and so on. We already know what 1 to n is, right? That's a vector that goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 if n is 10. All right, so that's it goes through this vector 1 by 1, 1, 2, 3. So the first time I is 1, so it will display 1 squared. Then the second time I is 2, so it will be 2 squared, and so on, all the way up into and including n. So then n will be 10. It will display. I will be 10. It will display 10 squared, 100, and we should be good. Let's try that. Aha! Did it work? Squares up to 1, 2. Well, they look like square numbers to me. Yes, and indeed they are. Brilliant. All right. So now time for you to make it more interesting. I want you to not just print out the first squares. I want you to change the script to display the first 10 odd cubes. All right. So I don't want squares. I want cubes. And then I want the first 10 odd cubes. So I want 1 cubed, 3 cubed, 5 cubed, 7 cubed, and so on. So you're going to have to change the range that you are that you're looping over. All right. So have a go at that. I'll pause the video here, and you'll be able to have a go. All right. First 10 odd cubes. Let's see what we can do. So first, we want to change it to output I cubed. I suppose we could say it's cubes I, and then I want to go up in 2s, right? I want to do 1, 3, 5, and so on. So I have to go up in 2s, and then n being 10 isn't good enough anymore. N needs to be 20, I think. So we can change that there if we want, or you could have done 2 times n. That would have worked as well. Let's run this and see whether it works. So we've got, okay, we've still called it squares up to escape. Let's ignore that, it's our little secret. We've got 1 cubed, 3 cubed, 5 cubed, 7 cubed, 9 cubed, 11 cubed. It's a nice number, isn't it? And so on. Good. So it looks like the cubes work nicely. So that's a for loop. I'm now going to show you a while loop. So this will do something until something changes or while something is true. So let's create a new function. This we're going to call count up to. Sorry, a new script. I think I might have said, oh no, I beg your pardon. This is going to be a function. Count up to. This will be a function. It's going to be a function, and again, you're going to be able to copy and paste this from the GitHub. I'm going to do it line by line, type it out so you can see what why I'm doing each line. So I'm going to count up to n. It's not going to return anything. Some functions return things. Other functions just do things. You know, they just print things out. And I can put the end of my function in already. I can even add a bit of space if I want. All right, so I'm going to start by letting I equal 1. And then I'm going to display I. All right, so far so good. The point of this function is that it's going to count up to a particular number. It's going to go 1, 2, 3, 4, 5, all the way up to n. It's going to display the numbers up to n one by one. Now, this is not by any stretch of the imagination a good way to do this. We already know how to print the numbers 1 up to n, right? It's just 1 colon and then n. But for the purposes of showing you how a while loop works, let's do it like this. So we're going to display I, and then while I is less than n, I'm going to ask it to let I be I plus 1, and then display I. That's the end of the while loop, and indeed that's the end of the function. Let's have a think about what's going on here. All right, so we're counting up to n. So the first time, all right, I equals 1. Let's display I. Good, I is 1. So 1 has been displayed. While I is less than n, right, let I be I plus 1. Right, so now I is 2. Display 2. Perfect. N. So we go back to the top, and the while loop goes round and round and round and round. While I is less than n. Is I still less than n? Well, yes, 2 is less than 10, right? So in it goes I equals I plus 1. So now I equals 2 plus 1, which is 3. Display 3. Good. End the loop back at the top. And so we keep on going round and round and round until eventually I is we've displayed 9, while 9 is less than 10. Yep, good. Let's say if n is 10, while 9 is less than 10, good. Then we have I equals 9 plus 1, so that's I is now 10. Display 10, good. While 10 is less than 10, no. 10 isn't less than 10, so that's it. That's the end of the loop. It doesn't do any more. So I'm going to let you go ahead and copy and paste this and run it and see that it behaves like you think it should behave. And then we'll come back and have one last look at this, particularly with breakpoints, which we looked at earlier. And then I'll give you a challenge for the rest of the session. And don't forget that in order to run this function, you're going to have to type count up to and then a number. You can't just go up here and click run because, of course, it's a function. But I'll give you some time to work on to try it out now. All right, so let's see whether this works. Count up to 10. Aha! 1, 2, 3, 4, 5, 6, 7, 9. Brilliant, it works. I said I'd mentioned this in the context of breakpoints. Remember, breakpoints allow us to stop the code as it's going. Remember, we looked at that earlier. I click breakpoints and then set a breakpoint. So I could choose within this while loop, maybe at line 7 here, before line 7 is executed, I'm going to place a breakpoint. Remember, you can do breakpoints set clear like this, and you put a little red disk over here, or you can use F12 on the keyboard, which I'm pressing now, to toggle the breakpoint. If I now try to run the function, remember again that pressing up shows you all the things that you've run before. Aha, so now it runs down and it stops when it hits this point. So we can see, right, what's the value of I right now? Hover over I. I is 2. Okay, we continue. Next time round, what's I now? 3. 4. 5, and so on. And we can keep on going and going. If you ever want to quit debugging and stop this whole process, you can just press quit debugging and it just kills the whole program. That's how that works. All right, I'm going to clear the breakpoint. And I'm about to set you a big challenge. So if you want to break at this point, take one now, and then when we come back, we will look at the challenge, which will be the last thing that we do in today's session. All right, I'm going to tell you about now the collapse conjecture. This is something that I want you to try and write, a program that does this. The collapse conjecture, and you can see I've given a link to Wikipedia here, is a famous mathematical conjecture about a sequence which starts with a positive integer n, and then the next term in the sequence is given by Collat's function. That's the function we've already written. Remember, Collat's function, let's go back to Matlab, is the function which, here is it, which if the number is even, halves it, and if it's odd, it does 3 times n plus 1. That's what the Collat's function does, either halves it or does 3n plus 1. So you start with a positive integer n, and then the next term in the sequence is given by the Collat's function of n. And you keep on going and going and going, each time taking that number in the sequence and then putting it back into the Collat's function. And eventually you get to number 1. That's the conjecture. It's unproven, which is really fun. But the conjecture says that for whatever positive integer you choose, you will always end up with the number 1. So, for example, for n equals 5, well, 5 is odd, so you do 3n plus 1, which gives you 16. 16 is even, so you halve it, you get 8. 8 is even, you halve it, you get 4. 4 is even, you get 2. 2 is even, you get 1. So your job is to create a new function, the so-called Collat's conjecture of n. Right, so we have Collat's function, which does this function here that takes you from one term to the next term. I want you to create a new function, Collat's conjecture, which takes a starting number n here and displays the terms in the sequence. All right, so one by one, I want it to display or to print out the next term in the sequence every time until it gets down to 1. So I want to see the whole sequence. So I want you to have a little bit of a think about the logic that you need to do that. There are some hints down here, and you're going to have to use a while loop. And I'll let you read the hints if you want them. To get a better sense of the paths of these numbers, there's a nice there's a nice XKCD graphic. Let me try and find that for you. Which shows you the here's some of the paths. Okay, fine. I mean, you can go and enjoy this joke if you want, but you can see some of the paths here. Like 7 takes you this way. In fact, many they also go through 16. Interesting. So I'll let you enjoy that. And that is the challenge. So go ahead, enjoy that. Instructions are here. If you want help, let me know in the chat, and then come back and I'll show you how I did it. But I imagine this will take a little while, so don't worry. No rush for here at all. Take your time. All right, so maybe you had a go at using this. This is how I would do it. So I'm going to take a new, have a new function, Collat's conjecture. So this is a function Collat's conjecture, which takes a start number and obviously have an end. And then we're going to keep on going. So we have our first number n. And then this is how I would do it. We need to keep on looping round so long as n doesn't equal 1. And yes, you might have had to find out what not equal to is in Matlab, but it looks like that. Yes, I know it's weird. That's Matlab for you. We can probably end in while we're at it. While n doesn't equal 1, let's let n be Collat's function of n. And let's display n. I reckon that ought to do it. We don't need a semicolon there. Let's just let me just check that works. Let's see. Nice. Oh, okay, I don't need this extra one down here. All right, let's see what the logic is here. So the logic is, here's the function. It takes an input number n. and then while n doesn't equal 1, so we're going to run collat's function on n, and then we're going to let the output of that be the input the second time round, right? N equals collat's function of n, display n. Does that make sense? You see, we've let the output of this function be the input the next time round by letting n be equal to the output the previous time. I think that makes sense. So n comes in as 5, say. N doesn't equal 1, all right? So now n is going to be equal to collat's function of 5, which is 16. So now n is 16, display 16, goes back around to the top. Well, n doesn't equal 16, all right? So now we have collat's function of 16, which is 8. So now n is 8, and we can go round and round and round. It displays it all the way until the end. So that is how I would do that. And then there's a little extension at the end, which I'm not going to go through, but if you would particularly like to do that, why not write a script just for the key, collat's trials, which loops through the numbers 1 to 10, printing out the collat's path every time. Maybe you'll find which number has the longest path, that is the length of the sequence, and which has the shortest path. And then finally, I'm going to give you just a peek at what we're going to be doing in the final session, part 3. So in part 3, there's going to be an emphasis on data analysis. I know many of you will be interested in using Matlab for data processing. So in part 3, we're going to take a large amount of data. We're going to try and import it, and we're going to do some data analysis with it. So this will take us quite a long time, actually. It doesn't look like too much, but this will take us a good chunk of time. And then I'm also going to show you just a little bit of linear algebra, mostly because you can't possibly do a Matlab course without seeing a little bit of linear algebra. So that's all coming up in part 3. Good job on today. I think we saw some if statements, we saw some for and while loops, and we had some fun thinking about how we might write the collat's conjecture. We had a bit of fun doing some pretty ugly plots, but we'll do some more plotting tomorrow when we do the data analysis, and so you'll have a chance to plot some more stuff. And of course, we wrote some functions as well, a very powerful thing in Matlab. So I hope you enjoyed today's session, and I will see you again for part 3 next time.